Okay, now I want to talk a little bit about range, which is the idea of what is the delta x? How far horizontally does our object go? And frequently we think back to that initial launch angle to talk about this, and I want to talk a little bit about the range equation, and at the end of this video I will actually work through the derivation of where this equation comes from. So the first thing to know is that whenever we draw these pictures, you can see that our starting height and our ending height are the same. This equation is only true, only valid, if your starting and ending heights are the same, and that's really explicit when you see the derivation. And I point that out because I see a lot of students make the mistake of using this when that isn't true. So this is an equation that I don't like putting on the equation sheet since people grab it when it's not the appropriate tool. So one thing to note is that when we pick a launch angle, we actually find that for a given delta x, there are two different thetas that get us to the same delta x. So for instance, the one I've picked, 30 degrees gets you there, and again, that's your launch angle, but so does 60 degrees. And if we look at this closer one, 15 and 75 both get you there. So if you add these two angles, you actually get 90. So 45 degrees is the special one where that gets you as far as possible for a given launch speed, as long as, again, your initial height and your final height are the same. If your initial height and your final height are different, then the greatest distance will be for a different angle. That calculation is a little bit harder to do, though it is possible based on the math that you know. So we have this equation, and where r is going to be this delta x. And part of why I like calling it r is, again, that this is a special variable only true if, again, your initial and final height is the same. So it depends on your initial speed squared, and this is where we go back to notation, right? When you see this, you should know, this is my initial speed. That's what that means when I see v0 squared, and it's obviously a magnitude. It's not an x component, it's not a y component, it's the magnitude. And then it's sine of 2 theta, where theta is again going to be your launch angle. And normally you're not going to see equations that involve, say, 2 theta in this class. It's normally just theta. That's actually coming from a trig identity. So again, that's why we're going through the derivation. And on the bottom, you see gravity. Now ideally, you would want to look at an equation like this and ask yourself, does this make sense? Does this depend on the variables that I expect it to? Now, you should expect this to depend on your initial speed. You know, imagine that 2 people are both throwing softballs in the quad, and these 2 people throw at the same angle, but one is much better at throwing than the other. The person who can throw it with a greater speed expects their ball to go farther, even if they've thrown it with the same angle. Next, you kind of have a feeling that the angle matters. Imagine crouching down on the ground and throwing perfectly horizontal. The ball doesn't go very far. Now again, the only reason it goes a distance at all is because you actually weren't exactly on the ground. Now imagine instead throwing it straight up. Again, it won't go very far. But if you pick an angle with respect to the ground, it goes a better distance. Finally, gravity matters here. That if we're floating out in space and you threw the ball, it would just keep going forever. So one thing to keep in mind is that we might look at problems where you're doing projectile motion on other astronomical objects. So for instance, projectile motion on the moon or on another planet. And in that case, you would use the gravitational acceleration of that moon or that planet in this equation. Okay? So now there's something to kind of think through here, that we've already talked about how time connects what's happening in y and in x. So when we think about range and why it goes a certain distance, v0 sine theta, so this is your y component of the initial speed, right? V initial y, controls the amount of time in the air. If I wanted to maximize the amount of time that my ball spends in the air, I would just throw it straight up. It doesn't matter how far it goes. So the closer your angle is to 90, the higher it goes, which means the more time it spends in the air. But v0 cosine of theta, which is your x component, this one now is controlling the horizontal travel. for a given time. So remember that we have uniform motion in x, so it's traveling at a constant speed given by that initial component in the x direction, and so the longer it spends in the air, the farther it can travel horizontally. So y component gives you time in air, x component tells you how far you travel for that time. Again, it's time that really pulls these two things together. So I want to talk you through something that kind of relates here. Let's say we have a situation where I have a nice water balloon catapult that I've taken out into the quad, and I see that the mathematicians have a window that I can potentially hit. So I want to soak the mathematicians with my water balloons. I promise that I'm friends with them. They'll think this is hilarious. But what I need to do is actually adjust my angle to find at what point my water balloon gets in the window. Obviously, it's not going to go in the window every time. I actually have to control the variables. So maybe there's one specific point where I leave my catapult, and the catapult always fires at the same initial speed. So all I can do is adjust the angle. So my first water balloon barely hits the building at all. It doesn't make it to the window. What would I do? Well, it looks like I need to adjust the angle up. I need a larger theta. Okay. So we adjust the angle up. Again, I see that it hits below the window. It's hitting the building, it hit higher up, but it didn't hit the window. So again, I'm not adjusting the speed, but I'm going to tilt the angle up a little more to try to get it in. And now, well, actually, if you look, it went higher. And this height would have been enough to get it in the window, except that it wasn't to the building yet. This was still in the middle of the air. By the time it got to the building, it was even lower than the previous trajectory. If I tilt it even further up, well, obviously it's going to go higher, but now it's not even going to hit the building. So this is something to think about, that each one of these, the window's at the same height, my initial height is the same, the speed is the same, the distance that it has to travel is the same, but the theta is different. And now you could ask the question, gee, well, is it even possible with this speed to hit the window? Maybe not. So please think about this, that when you're doing projectile motion questions, frequently you're talking about the top of the trajectory or the end of the trajectory. That's not always the case. Like in these two situations, we have the top, right? This is y max here. But where it actually got to my distance, right, where it actually hit the building is down here. This isn't y max. But if I call this T1, we would have x1 equals d, and we have some y1 that isn't equal to y max. The same thing would be true for the black curve. And again, you see that there's a different position of y max. It spends a different amount of time in the air. And in fact, if you look, it looks, if I was to try to continue these curves down, it looks like the black curve actually goes the farthest. So the black curve goes the farthest. That corresponds to a 45-degree angle. I drew these trajectories, so I know that that's actually true. If you look back here, that certainly looks like 45 degrees. But even a 45-degree angle is not going to get you in the window. So in this case, this initial speed can't possibly have me soak the mathematicians. I would need to move closer or change my initial height to get it in the window. So part of why I point this out is when I've given students calculation problems like this, I see them make the assumption that it's going in the window at the maximum height. And that's simply just not true. So if you know what the distance is, maybe it could go in the window. Let's say I increased my initial speed. Let's make that taller. That means that even if I go the same angle initially, it would go higher and boom, it would soak my mathematicians and make me very happy. So keep that in mind, that it doesn't necessarily hit your object at the maximum height. It doesn't have to. But there's just some coordinate xy where they share the same time, and that time is really important.